Good evening, everybody. Welcome to Chem 1211 with your host, me, Dr. White. How you doing? All right, today I'll be doing the review for Quiz 6. I've already sent out the password and for Quiz 6. Remember, you'll have until Monday, December 2nd to do Quiz 6 and upload it to Blackboard. Please upload it as a single PDF file, not a JPEG or other files, or I'll take off points. And before I forget, everybody have a happy Thanksgiving holiday and don't spend too much money on Black Friday. I probably will, but anyways, some good deals going on. But I don't know if I told you this, but in our family, the turkey isn't the only thing that gets stuffed. We do. Do we? All right, let's get going. Let's not get going. I closed the file. Hold on while I open something. All right, now it's open. Let's share it with you. All right, you'll see on your screen right now, Quiz 6 review. This is located, what you see on the screen, heavily, cleverly hidden in the lecture section folder of Blackboard and called Chem 1211 Quiz number 6 review. I have it both as a Word file and as a PDF file. All right, things you should know. Hint, you should know what is a Bronsted-Lowry acid, and that's a proton donor. You could also write down any substance that can donate a proton, H plus, to another substance, but it's easy to remember a proton donor, and a proton is H plus. Now, a Bronsted-Lowry base is a proton acceptor, again, H plus. If I'm a base, give me your protons. If I'm an acid, here, take my protons. I like my special effects. And you should know this. Don't worry about the Arrhenius theory. This has been, the Bronsted-Lowry has replaced it. Nobody uses Arrhenius. All right, now, you should know the chemical formula of some key acids. You should know HCl, hydrochloric acid, is an acid. H2SO4 is acid, sulfuric acid, and HNO3 is nitric acid. Now, strong bases are sodium hydroxide, NaOH, also known as lye. That's the old name. If you ever heard the term lye soap, fat was reacted with water and sodium hydroxide to make that soap. And that's why they call it lye soap. And KOH is potassium hydroxide, that's a base. Remember, a proton acceptor. And NH3 is ammonia, and that's the base. Now, I don't have down here, but another base you should know, because I talked about it, sodium bicarbonate, which is baking powder. You know, that comes in a little can like the red can Calmet. There's a brand made in Indiana called Gabler Girl. What a weird name. But anyways, you should know this. And if you watched the videos, you heard the story about how my father taught me to put baking powder and vinegar together, the little rocket ship, to have it blast off. I just remembered a picture of that in my mind, me doing it when I was about 6 years old. It's one of the nice things, and sometimes not always nice things, about having a photographic memory and pulling back memories decades ago, like it was just yesterday. All right, let's get back to chemistry. All right, now, turns out water can react with itself. And this is called the dissociation of water, and it's an equilibrium. And if you have two water molecules, the equilibrium is mainly on the left, but you'll form some hydronium ion, that's H3O plus, and hydroxide OH. And not the equilibrium constant, but KW. No, it's not named after me, Kenneth White. I wish it was, but it makes me feel good when I see KW, my initials. And that's the ionization constant for water. And you should know that that's H3O plus concentration times hydroxide concentration equals 1. Actually, I should have had this as 1.0 times 10 to the minus 14. Now, this is for room temperature, 25 degrees. At other temperatures, it's slightly different, but for our class, this is what we'll use. Now, when it comes to acids and bases, in an aqueous solution, there are the terms acidic, basic, and neutral. And you should know an acidic solution is with the concentration of hydronium ion, H3O plus, is higher than the hydroxide. And one way to remember this, remember when I put something in bracket, that's concentration, how much, moles per liter. So the hydronium H3O plus is greater than hydroxide for acidic. For basic solutions, sometimes called an alkaline solution, how many of you have heard of alkaline batteries? That's because the material in there is basic. Now here, a basic solution, the hydroxide ions is higher concentration than the hydronium. And you should know a basic solution, OH minus concentration hydroxide, is greater than hydronium ion. And that's a basic solution. And a neutral solution is a solution in which the hydroxide ion concentration is equal to the hydronium ion concentration. And that's called a neutral solution. So, acidic solution, hydronium greater than hydroxide concentration. Basic solution, hydroxide greater than hydronium concentration. Neutral solution, they're equal. Now, it's sort of hard to think about, well, if you have one is 1 times 10 to the minus fifth, and the other 1 times 10 to the minus 9, which one's greater or that? And that's tough. So someone came up with what's called the pH concept. This is probably one of the most important things I'll teach you this semester that you'll probably use often, or not often, but sometime the rest of your life. And the pH scale is a scale of small numbers that is used to specify molar hydronium ion concentration in aqueous solutions. By definition, pH equals minus the logarithm of the hydronium ion concentration. Now, as a special gift to you, if the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH is x. And that way you don't have to learn, and I don't have to teach you how to use the logarithm function on your calculator. Yay, Dr. White. Thank you. You're welcome. Now, the pH scale, important. Let me make it even more I'll be very subtle now. Don't you love when I'm subtle? Now the pH scale goes from 0 to 14. It's never less than 0. It's never greater than 14. I almost fired someone who gave me a report that I had to review before it was sent out to the research vice president, where he had a pH of 16 and 15. And I looked at him and told him, do you want to keep on working here? Don't ever give me a pH data higher than 14. He didn't calibrate the instrument correctly, and he should have known better. Master's degree chemist should have known better, even a bachelor's degree. But anyways, now at 7, you're at neutral pH. Anything below 7 is acidic. Anything above 7 is basic. The lower you get to 0, the more acidic something is. The higher you get to 14, the more basic something is. And here I say that. It's a logarithmic scale. So the difference between pH 6 and pH 7 is the power of 10 in the hydronium ion concentration. So it looks like a small difference, but really it's a large difference. All right, here's chapter 14, practice problems. And notice I have here identified the following as acid, base, etc. You can go look at it at your own leisure. Now, let's look at number 4. If a solution has the hydronium ion concentration, H3O plus in brackets, of 1.0 times 10 to the minus 3, what is the pH of that solution? And is it acidic, basic, or neutral? And if we look here, we're trying to initially find pH. We're given the hydronium ion concentration. pH minus the log of the hydronium ion concentration. We put that in. When this is 1.0 times 10 to the minus x, the pH is x. In this case, x is 3. The pH is 3. Is that acidic, basic, or neutral? Here's the scale you should know. Below 7 is acidic, 7 is neutral, above 7 is basic. I hope you all know 3 is less than 7. Isn't that hard math? And it's acidic. And I have a few more like this. Now, let's look at number 7. If a solution has hydroxide OH minus concentration, that's what the brackets mean, moles per liter concentration of 1.0 times 10 to the minus 3, what is the pH of the solution? Is it acidic, basic, or neutral? Now you need 2 steps. Why? Because pH is minus the log of the hydronium ion concentration. Oh, look, Dr. White was being mad and cruel at his students. He didn't give us the H3O concentration. He gave us the hydroxide. So in the first step, you have to use hydronium times hydroxide equals 1.0 times 10 to the minus 14. That's Kw, the equilibrium, not the equilibrium, the ionization constant of water. Now we want to solve for H3O plus so we can find the pH in the second step. So what do? To get rid of the OH, we divide by it. But whatever we do to one side, we have to do to the other. So we do. Anything divided by itself is number 1, cancels out. We're left with hydronium ion concentration equals 1.0 times 10 to the minus 14 divided by the hydroxide. And we'll put that number in, which we know is 1.0 times 10 to the minus 3. Due to division, you get 1.0 times 10 to the minus 11. Are we done? No. We're trying to find pH. This is just the hydronium ion concentration. Now you go to step 2. Oh, someone stole the number 2 from here. Please return it. Well, that was a bad joke. Sorry. But anyways, that should be step 2. It's very tiny. You have to use your magnifying glass to see it. But pH minus the log of the hydronium ion concentration, we calculated what that is, 1.0 times 10 to the minus 11. When the pH is 1.0 times 10 to the minus x, or the hydronium ion concentration, 1.0 times 10 to the minus x, the pH is x. In this case, x is 11. The pH is 11. Now, is this acidic, basic, or neutral? Let's go back up here. Below 7 is acidic, 7 is neutral, above 7, which 11 is, it's basic. And therefore, it's basic. Now, one thing I didn't have opened up, if you look on your screen now, you'll see important information for quiz 6. The last page of the quiz 6, this will be given to you. Have the definition of pH. I remind you, if the hydronium ion concentration is 1.0 times 10 to the minus x, the pH is x. I give you the ionization constant for water. And then I'll talk in a little while how to calculate with titration molarity of acid or base. Now, one thing I should mention, if you have a neutral solution of water and you add some acid to it, the numerical value of the pH will drop because it becomes acidic. So when you add acid to a neutral solution, the pH numerical value gets lower, below 7. Now, if you have a neutral solution, you add a base, the pH will become higher because the solution will be basic. Again, if you add a base to neutral solution, now the pH will increase because the solution is now basic. You added a base. Now, an important aspect, which I'm not going to go that much into, is buffers. Buffers are a solution that use equilibrium or Chatter's principle to have a equilibrium. So if you shift the equilibrium by adding an acid or base, small amount, it shifts in such a way that it brings it back to neutral pH, or it stops the pH from changing. So what you should know is a buffer solution is a solution that resists major changes in pH when a small amount of acid or base are added to it. Now, the last thing I'd like to talk about is titrations. We have what's known as the neutralization reaction. And if you take an acid, any acid, and you add to it a base, and usually with strong acid and strong base, the K equilibrium is very high, it's mostly to the right, you'll get a salt. and here's the salt. Now, what it means to neutralize something, you bring the pH to 7. And you can measure using a pH indicator. And the most popular one is phenolphthalein. It goes from clear to red or wine color. When it goes clear, it's acidic. When it becomes basic, it's a red or wine color. And that tells you when you've hit one molecule above either acidic or basic. At neutralization, moles of acid equal moles of base. These are all reacted. And for a monoprotic acid and base, which that's all we're doing in this class, I have the equation milliliters of acid times molarity of acid equals milliliters of base times molarity of base. Now, if we look at, let's make sure you are looking at this, and you are. Sometimes Zoom, you have to check to make sure you really have sharing what I'm supposed to be sharing, and I am. Let's look at 13. Hint, you should know how to do this. Hint, if you have to add 115 milliliters of a 0.333 capital M HCl hydrochloric acid solution to neutralize 211 milliliters of a sodium hydroxide solution, NaOH, what is the molarity of the NaOH sodium hydroxide solution? So we're trying to find the molarity of NaOH. Remember, that's a base. We're given the milliliters of NaOH, and we're given the milliliters and the molarity of the solution to neutralize it. At neutralization, milliliters of base times molarity equals milliliters of acid times molarity of acid. Well, we're trying to find the molarity of this base. So how do we get rid of the milliliters of base? Divide by it. Anything divided by it equals the number 1. But whatever you do to one side, you have to do to the other. And I did. This cancels out. We're left molarity equals milliliters of acid times molarity of acid divided by milliliters of base. And here we have 115 milliliters of HCl, the acid, 0.333 molarity HCl, the acid, divided by 211 milliliters of the base. Remember, when you multiply and divide, you get the same number of significant figures as the number with the least significant figures. And Dr. Whiteson is right again, 3, 3, and 3. And my answer is 3. And that's how you do it. Now, yesterday, one of your colleagues came to my office hour and said, how do you do this kind of problem, and might it be on the test? And the answer is, I'll show you how to do it. And I forgot to put it in the problem set. Bad, Dr. White. Bad, Dr. White. So let's do one. All right, for the following equilibrium reaction, phosphoric acid H3PO4 plus KOH gives potassium phosphate plus water. And you have to identify each one of those is either acid base, conjugate acid, or conjugate base. By definition, everything on the right of this equilibrium is the conjugate, and I'm going to just abbreviate. So immediately we know G and H are conjugates. Now, what is a conjugate pair? That's something that differs by one hydrogen. Ignore the alkali metals or alkaline earth metals. So if we look at this, here we have a phosphorus, here we have a phosphorus. So that's got to be a conjugate pair. And that leaves this to be the other conjugate pair. F and H, ignoring the potassium, only differ by a hydrogen. Same thing, E and G. Now, why do we need to know the conjugates pairs? Because when we go from E this way to G, does it lose a proton E or gain it? Now, to make your life easier, just look at, does it lose a hydrogen or gain? It goes from 3 to 2. Something that loses or gives up a proton, donates a proton, is an acid. So E is an acid. Now, if we look at going from G to E this way, it goes from 2 hydrogen to 3. Does it lose a hydrogen, H plus really, but think of it hydrogen, or does it gain, accept the proton hydrogen? Well, it goes from 2 to 3, it accepts it. And something that accepts a proton is a base. So that means G is the conjugate base. Now, let's look at F and H, the conjugates. When it goes from F, KOH, to H, H2O, does it gain a proton, just think hydrogen, or lose one? It goes from 1 to 2. It's gained or accepted it. What's a proton acceptor? A base. So this is a base. And now we're left with one more to do. And you, by a process of elimination, you should know what it is, but let's make sure we did this right. When we go from H to F, it's conjugate. Do you lose or gain a proton? Count hydrogens. Go from 2 to 1. Oh, it's lost or given up or donated a proton. What's a proton donor? An acid. Therefore, H, because it's on the right side, is a conjugate acid. And with that, I'm done. Does anybody have any questions?
No, thank you.
Stick around for a sec.
Okay.
Well, with that, I'm going to log off, and if anybody has any questions, I'll answer them. But I'll be posting this video. Don't forget, I've already sent out the password for quiz 6. because of Thanksgiving, and I hope you all have a happy Thanksgiving and a happy Black Friday. You get some good deals if you're in the mood for it. I will, since schools close tomorrow at College of DuPage, Thursday, Friday, Saturday, and Sunday, I've set the due date for quiz 6, Monday at 6 p.m. You had all day today to do it. You'll have all the time if you want till Monday, 8 p.m. And don't forget, hand in your labs. And with that, I'll say gain gesund, going health in Yiddish, and you know what's coming next. Bye now. Still there from Brandon to Beverly Hillbillies. Bye. Bye.